Picture this. You're part of the first crew heading to humanity's moon base. You've trained for years, the landing is flawless. You descend the ladder, boots sinking into gray lunar dust, and then silence. No hum of electricity to warm the habitat, to drive the oxygen, or to pierce the lunar darkness with light. In an instant, the dream collapses into a nightmare. No power means no life. The mission ends before it even begins. The moon isn't just our closest neighbor, it's our gateway, a proving ground for the technology, infrastructure, and global coordination we'll need if humanity hopes to survive beyond Earth. It could become the refueling station for deep space missions, the launch pad for exploring Mars, maybe even humanity's first off-world city. But here's the blunt truth. If we can't figure out how to power a base on the moon, the body closest to us in the cosmos, then talk of Mars colonies or asteroid mining is nothing more than science fiction. So, how do we solve it? Section 1. The power problem. Here's the challenge no one can escape. The moon has nights that last 2 full Earth weeks. That's 354 straight hours of pure darkness. When the sun drops, it doesn't fade gently like on Earth. It's just gone. No atmosphere means no twilight and no afterglow. 1 second you're in blinding light, and the next you're swallowed by an endless black sky. On the far side of the moon, there's not even Earth hanging above to give you a dim reflection. It's the kind of dark where your hand disappears right in front of your helmet. And then comes the cold. Temperatures fall to negative 280 degrees Fahrenheit, or negative 173 degrees Celsius. At that level, steel turns brittle, electronics seize up, and your breath would freeze in seconds if your suit failed. Any astronaut caught outside would become a statue of ice and silence. During those nights, the sun, our usual power source, is worthless. Solar panels? They become nothing more than frozen sheets of glass and metal. What about batteries? In theory, you could try, but to survive 2 weeks, you'd need to stockpile energy for every system on the lunar base, such as oxygen pumps, heaters, computers, and lab and communications equipment. The battery banks would be larger than anything humanity has ever built. And then you'd have to somehow keep them warm enough not to die in the cold. That's not just hard, it's nearly impossible. Which leaves one conclusion. If we want to survive on the moon, we need a power source that never sleeps. One that laughs at the cold, doesn't wait for daylight, and doesn't care about the moon's position in its orbit. Section 2. Nuclear power, proven in the darkest places. Before we stake human survival on the moon, we need a power source with a proven track record of reliability. One that doesn't gamble with life support, quit after a few nights, or depend on resupply missions that may never arrive. That source is nuclear power. For over 60 years, compact reactors have powered submarines deep beneath Earth's oceans. Crews live for months sealed inside steel hulls, surrounded by crushing pressure and absolute darkness, with no sunlight, air, or immediate backup or rescue. Their lives depend entirely on one thing, a steady nuclear core. And it worked every single time. And submarines are just the beginning. Nuclear has been proven again and again in the harshest environments humanity has dared to enter. Look at spacecraft. The Voyager probes, launched in 1977, are still transmitting from interstellar space nearly 5 decades later. They are powered entirely by nuclear batteries. Cassini orbited Saturn for 13 years with nuclear energy. And even today, the Curiosity and Perseverance rovers crawl across Mars with nuclear power, immune to the dust storms that crippled their solar-powered predecessors. And it wasn't just probes and rovers. In 1965, the United States launched SNAP-10A, a small nuclear reactor that successfully operated in orbit. The Soviet Union followed by deploying dozens of compact nuclear reactors aboard radar satellites, proving nuclear power could be miniaturized, hardened, and ran reliably in the vacuum of space. Back on Earth, America's own Navy has carried the same torch. The USS Enterprise, the world's first nuclear-powered aircraft carrier, sailed for over 20 years without ever needing to refuel. Its successors, the Nimitz-class carriers, are floating cities of thousands of sailors, powered by twin nuclear reactors that allow them to deploy for decades at a time. They generate enough energy to launch fighter jets, run entire onboard communities, and project American power anywhere in the world. All this completely independent of fuel supply chains. Across oceans, in orbit, and on Mars, and at the edge of interstellar space, nuclear has delivered steady power where failure meant the end. The same principle applies on the moon. Swap seawater for lunar dust, and the challenge is nearly identical. No outside support, no margin for error, and no second chances. Nuclear power has already kept people and machines alive in places designed to kill them. Section 3. Price tags and payloads. Every ounce sent to space comes with a price tag. The James Webb Space Telescope cost about $10 billion to build and launch, and it weighed just over 14,000 pounds. Do the math, that's around $700,000 per pound. NASA's Perseverance rover? That mission cost about $2.7 billion for a machine that weighed just over 2,200 pounds. That's a jaw-dropping $1.2 million per pound delivered to Mars. Now scale that up. A small modular nuclear reactor with shielding is projected to weigh roughly 13,000 pounds. At that projection, sending just one to the moon could cost between $9 to $16 billion, and that's before building the base around it. Sounds outrageous until you remember the International Space Station cost more than $150 billion, and it still depends on constant resupply from Earth. A lunar reactor could actually pay for itself in less than a decade by cutting off that dependency. But price is only half the battle. The real challenge is delivery. Back in the Apollo era, the Saturn V rocket was the workhorse that carried us to the moon. It could lift about 260,000 pounds into lower Earth orbit. But each launch cost the modern equivalent of over $1.6 billion, roughly $6,300 per pound. Saturn V was the most powerful rocket ever built at the time, but was also one of the most expensive. The space shuttle promised to lower those costs. On paper, the incremental launch cost worked out to about $6,400 per pound. But if you include the full cost of the program, development, maintenance, and infrastructure, the true average was closer to $27,000 per pound. Reusability helped, but it wasn't the leap forward NASA had hoped for. Falcon 9 finally changed the economics. Thanks to reusable boosters, it dropped launch costs to around $1,500 per pound. Next comes Starship. SpaceX's next-generation rocket is designed to haul 100 to 150 metric tons. That's 220,000 to 330,000 pounds in orbit in a single trip. Musk's ultimate target is about $10 per kilogram. That's only $4.50 per pound. Starship could rewrite the economics of spaceflight and make hauling reactors to the moon not just possible, but practical. NASA's Space Launch System, or SLS, is another powerful contender. Block 1 is built to deliver 95 metric tons beyond Earth orbit, and future versions will top 130 metric tons. The truth is, we may need both Starship's success and NASA's Space Launch System to complete this mission. Multiple launch systems working in parallel to deliver not just one reactor, but the entire chain of habitats, labs, and supply modules that make a permanent moon base a reality. Section 4. How lunar nuclear power could transform life on Earth. Here's where it gets really interesting. Lunar nuclear power doesn't just help astronauts survive, it could transform life back here on Earth as well. The same technology that powers a moon base could lead to safer, smaller nuclear power sources for communities in desperate need. Imagine advanced microreactors, compact factory-built systems that don't require massive infrastructure or constant refueling. Instead of billion-dollar plants buried in red tape, we're talking about portable units that could power a neighborhood, hospital, or even a small city. For communities without steady access to electricity, this could be transformative. A single microreactor has the potential to provide reliable power for essentials like clean water, internet access, and lasting economic growth. The leap in quality of life would be measured in not just dollars saved, but also in decades of progress gained overnight. Island nations battered year after year by hurricanes could finally have power grids that don't collapse when the winds rip down transmission lines. A microreactor can be shielded, hardened, and designed to operate independently, keeping the lights on when diesel fuel shipments can't get through. The same applies to remote Arctic villages or disaster zones cut off from the grid. For them, nuclear isn't a luxury, it's survival. And this doesn't replace renewables, it supercharges them. One of the biggest challenges with solar and wind is storage. Microreactors could provide the baseline power, while renewables would fill in the peaks. Together, they would act like a giant, resilient battery, steady, reliable, and nearly impossible to take offline. Also, I know what you're thinking. What happens if we go the way of the dinosaurs? Or some politician leans a little too hard on the wrong red button? That's when a moon base stops being NASA's science fair project and becomes humanity's second heartbeat. Section 5. Why humanity will need nuclear power on Mars. Because Mars makes the moon look easy. Nights can last for weeks. Temperatures plunge below -200 degrees Fahrenheit. Dust storms grow so massive that they swallow the entire planet, turning day into night for months at a time. Additionally, we've already seen the devastation that Martian dust storms can unleash. Remember Spirit and Opportunity, the twin rovers that landed in 2004? Both were solar-powered. They were supposed to last 90 days, but they kept going for years. That is, until dust storms finally smothered their panels. Their successors, Curiosity and Perseverance, run on nuclear power. When storms of similar magnitude swept across Mars, these rovers kept crawling, drilling, and sending back data to our blue planet. That's the difference nuclear makes. One generation of rovers became history, the other is still alive today. Now imagine scaling that to humans. On Mars, a dust storm doesn't just end a mission, it ends lives. And unlike the moon, which is just 3 days away, Mars is a 6 to 9 month journey. There is no quick rescue and no emergency resupply. If the power goes out, it's game over. That's why NASA and the Department of Energy are developing fission surface power systems, or compact reactors in the 40 to 100 kilowatt range, with the first prototype planned for the moon by 2030. The moon is the only practical proving ground to test this in the field before attempting to sustain nuclear power on Mars. And if that sounds like science fiction, remember the hit movie, The Martian. Watney didn't survive on potatoes and duct tape alone. His real lifeline was nuclear. When the solar panels were useless, he dug up the RTG, the little nuclear generator buried in the sand, and used it to keep himself alive through the cold and dark conditions. That wasn't Hollywood magic. That was science imitating the very systems NASA already uses. The moon isn't just our neighbor, it's our testing ground. Prove nuclear power there, and Mars isn't a death sentence. It's the next step. Here's the kicker. This isn't science fiction. NASA, the Department of Energy, and private companies are already building prototype reactors. If timelines hold, the first lunar nuclear reactor could be up and running before 2030. So what do you think? Is planting a nuclear reactor on the moon humanity's smartest next step? Or is it the riskiest gamble we've ever taken in space? Drop your thoughts in the comments. If you want to dig deeper, click the QR code on screen to grab our companion book. Don't forget to like and subscribe if you want more deep dives into the future of space and science. Until next time, stay curious.